Hello, I'm Wolfgang Schwert with RAS Engineering, and welcome to the economic sense of high-performance buildings.
RAS Engineering strives to test the performance of building elements used during construction to provide high-quality results with the belief that testing and discovering energy-efficient solutions with fast payback is not only possible, but makes financial and economic sense.
Economic Sense of Backup Window Series, Episode 2, Pollution Control.
The envelope of a building, which is the exterior surface of a building, is the shield protecting the occupants from the environment. In addition, elements like windows have a great impact on air conditioning performance and drastically affect the energy efficiency of a building. In this Smart Window Testing series, we will prove that restoring your building with energy savings in mind makes a lot of economic sense. On the last episode of the series, we will evaluate the economic benefit of these tests, compiling all the testing results from the series.
This side of the mock-up simulates the exterior side of a wall on the building. On the interior view, notice that the top standard window is covered by the backup window. The backup window has several distinctive features. You can see how deep and solid the frame is. This window allows for high impact. This is valuable in the event of hurricane winds preventing breakage or blast explosion. Demonstrating with a hammer, the window does not break, but the glass in the standard window would. The window also has insulation inside on the frame. There is no contact in between the metal of the window with the exterior, meaning there is no thermal bridging that transmits the heat from outside into the metal, reducing transmission of heat, sound, infiltration of moisture, and pollutants.
Today we are running a particle infiltration test, measuring the penetration of contaminated air between both a standard window and a backup window. We will then calculate the savings based on the difference of particle infiltration.
This is the exterior part of the window mock-up showing the chambers attached to the exterior. We will run smoke into each chamber and pressurize it. Then we will go to the other side of the mock-up wall and measure the particles that pass through each of the windows. The top chamber has the standard window shielded by the backup window, and the lower chamber has the standard window alone. We will test the standard window now. The fog machine produces smoke which is dragged through the ductwork using a fan. As you can see, the smoke is coming through the window, which is an example of poor caulking and sealing on this standard window. As the air with the smoke is passing through the chamber, we are going to measure the particles that are leaking through the standard window. We are going to compare the measurements we are taking on the standard window with the results from the backup window. Now we will repeat the same test on the backup window. We will use the same amount of smoke and test the particles that leak through. Finally, we remove the air chamber to show the remaining smoke that could not pass through the complex path created by the extra sealants.
Now, let's take a look at the building code.
Indoor air quality requirements are ruled by RAS 62. The major building codes in California, Florida, and New York adopted this standard. Regarding the classification of the clean room, that's regulated by ISO and ANSI.
And let's do the math.
We will now report the results for the pollution test on the standard window and the backup window. The perimeters of these small windows are 74 inches each, and we will report 5 different particle sizes for each test. We will begin with the data for the standard window, which is representative of any standard window in use today. As you can see, a large number of contaminants pass through the standard window. Now we will compare the results of the backup window. The difference in these results is very significant, and the number of contaminants that pass through the backup window is greatly reduced in comparison. Small particles of 0.3 micrometers have a 48% reduction in pollution between the two windows, and infiltration rates decrease rapidly with the particles of larger sizes, with the 2 micrometer particles at 96% and the largest particles at 99% infiltration rate reduction. Now, based on the substantial improvement of indoor air quality, we are going to compare and assume certain costs here, because it is difficult to estimate the health of the occupants. You can see, by changing the standard windows, we increase the time of replacing the air filter from 11 days to 36 days. With that in mind, we save money on changing the air filter. In a contaminated environment, we assume there are 10 sick days per year, and in a healthy environment, we assume only 2 sick days per year. The loss of revenue due to sick days is estimated at $960. We also assume 3 visits to the doctor in a contaminated environment, while in a healthy environment, we assume only 1 visit per year. The savings in healthcare costs comes out to $240 per year. In total, by improving the indoor air quality by installing a backup window, we get $1,775 in savings.
Thanks to Green Bee for letting us test the backup window. If you would be interested in backup windows for your building, check them out at www.greenbee.solutions. If you'd be interested in contacting RAS Engineering for any services for your building, please check us out at www.ras.engineering. Links in the description below. And please follow our YouTube channel for the latest state-of-the-art testing videos on new solutions to improve your building and turn it into a high-performance building. Thanks for watching.
To receive alerts about monthly episodes of research and development for high-performance buildings with economic sense, sign up at www.ras.engineering.